Welcome to the deep dive. Ever stop to think if all this right now is just a really elaborate computer program?
Yeah, it's a wild thought, isn't it?
Definitely. It's an idea that's been kicking around for ages, from philosophers like Descartes and Berkeley, right up to modern thinkers like Bostrom and, well, obviously the Matrix.
Right, the Matrix kind of put it on the map for everyone.
Exactly. But today, we're not just, philosophizing. We're actually diving deep into a physics paper that throws some serious science at this simulation hypothesis.
We're looking at Franco Voss's paper, Astrophysical Constraints on the Simulation Hypothesis for this Universe. Why it is nearly impossible that we live in a simulation.
Quite a title.
It gets straight to the point. And for anyone interested in the actual nuts and bolts, this paper uses fundamental principles of physics.
Like information and energy?
Precisely, the link between information and energy, plus actual astrophysical observations, to figure out if a simulated universe like ours is even, physically possible.
So moving beyond the Twitter debates and sci-fi tropes.
Exactly. This is science tackling the big what if.
Okay, so give us the headline. What's the main takeaway for, say, a quick summary?
The big takeaway. The paper argues pretty strongly that it's physically impossible for our universe to be a simulation run by another universe that operates under the same physical laws as ours.
Impossible. Not just difficult, but actually impossible.
Based on these calculations, yes. Forget about waiting for better computers in the future. The sheer amount of energy and computational power needed is, literally astronomical.
Oh, wow, so even simulating something smaller, like just Earth.
Even simulating just planet Earth at any kind of realistic detail demands resources that are just mind-bogglingly huge. We're talking galactic scales of energy. It seems to push way past the limits of what our universe could possibly provide.
Okay, so the Matrix scenario run by our descendants or whatever is basically off the table, according to this analysis.
Pretty much, yeah. The only tiny loophole the paper leaves open is if the simulators, the ones running the program, exist in a universe with completely different physical laws. Fundamentally different.
Right, which is a whole other can of worms.
A very speculative one, yeah.
Okay, so how do they reach this pretty strong conclusion? What's the plan for this deep dive?
So we'll first break down their methodology. It relies heavily on some really cool concepts like the holographic principle.
Ah, yes, black hole physics bleeding into cosmology.
Exactly that. And this core idea that information is physical, that it has an energy cost, Landauer's principle.
Got it.
Then we'll walk through the three main scenarios the paper analyzes. First, trying to simulate the entire observable universe.
The whole shebang.
The whole shebang. Second, simulating just Earth, but down to the absolute theoretical limit, the Planck scale.
Maximum resolution.
Maximum is Earth. And third, simulating Earth again, but at a much coarser resolution, sort of the minimum needed to fool our current experiments.
Okay, sounds like a solid plan. Let's start with that foundation. Information is physical. What does that really mean in this context?
At its heart is Landauer's principle. Basically, any computation, anytime you store information, even just erasing a single bit in a computer, requires a minimum amount of energy expenditure.
So information isn't just abstract, it has a real-world cost in energy terms.
Exactly. It's tied to thermodynamics, to entropy. You can't get information processing for free.
Okay. So every particle's position, every interaction in a potential simulation, it all adds up energetically.
Precisely. And that leads us to the holographic principle, which, as you said, came out of black hole studies. It's always felt a bit sci-fi, hasn't it?
It really has. The idea that all the information in a volume is somehow encoded on its surface, it messes with your intuition. How does that help calculate simulation limits?
Well, the counterintuitive part is key. It says the maximum information you can stuff into a region of space doesn't scale with its volume, like you'd think.
Like filling a box.
Right. Instead, it scales with the surface area of the boundary of that region.
Like the 3D image on a 2D credit card. The surface holds the key to the whole picture.
That's a pretty good analogy, yeah. The paper then uses the Planck area, this incredibly tiny fundamental unit of area, like the universe's smallest possible pixel size.
Defined by gravity, quantum mechanics, speed of light.
The fundamental constants, yeah. And the Bekenstein Bound uses this to set an upper limit on the fuzziness or information content that can fit onto a given surface area measured in these Planck units.
So more surface area, more potential bits you can encode on that boundary.
Exactly. More potential information storage capacity.
Okay, so we have a limit on information based on surface area. How do we connect that back to the energy needed to run the simulation?
That comes from the link between information and entropy. We know the minimum entropy associated with 1 bit of information, right? It's related to Boltzmann's constant and the logarithm of 2.
Okay.
So the maximum number of bits you can store, Amax, is just the maximum entropy divided by the entropy per bit. This lets us estimate the total information needed based on the system's energy and size using the Bekenstein relation.
Right, so we can estimate the total bits needed. What about the energy cost to actually, write those bits into the simulation's memory?
That's where Brillouin Inequality is useful. It builds on Landauer's principle and gives a minimum energy cost, delta AE, to erase, or by extension, encode 1 bit of information. And crucially, this energy cost depends on the temperature, T, of the computing system.
So colder computers are more efficient, in principle.
In principle, yes. So you take the total maximum information, Imax calculated from the holographic bound, and multiply it by this minimum energy per bit, which depends on temperature. That gives you a lower bound on the total energy a day needed just to encode the state of the system.
The paper mentions this ratio, comparing this encoding energy E day to the system's actual rest mass energy A day. What's the significance there?
That ratio is fascinating. It shows that ELN major grows with the mass and temperature of the system. What's kind of mind-blowing is that even at incredibly low temperatures, like the cosmic microwave background temperature, the energy required just to describe all the possible states of a system vastly exceeds the system's own energy content once you get beyond really tiny objects.
So for anything macroscopic?
For anything macroscopic, yeah. Even for something with a mass of only about 25 protons, the energy needed to encode its state information, AE fans now it's accurate, already surpasses its own mass energy. It's like nature is incredibly efficient at being, but simulating it perfectly is incredibly energy intensive.
That's a huge hurdle right there.
It really is. The paper does note a caveat that Bekenstein's original bound doesn't fully incorporate gravitational self-interaction, which might matter for black holes, but the general point about information cost holds.
Okay, so with that framework information, costs, energy, holographic limits apply. Let's look at the first big test case, simulating the entire observable universe. What numbers do they plug in for our cosmos?
They use standard cosmological parameters.
Yeah.
The radius of the observable universe, about 14.3 gigaparsecs.
So roughly 46 billion light years.
Yeah, that order. Plus the average density of the universe, the critical density, and the Hubble constant for its expansion rate. From this, they estimate the total energy content of the observable universe, E1.
Okay. And what's the verdict on trying to simulate all that down to the Planck scale?
Well, they calculate the maximum information, IU1, that could possibly fit onto the holographic boundary of the observable universe using the Bekenstein bound. It's a colossal number, something like 10 to the power of 124 bits.
Right. An unimaginable number of bits.
Truly. Then, they calculate the minimum energy, EIU, needed to encode all those bits, even assuming the computer runs at the coldest possible natural temperature, the CMB temperature.
And the result?
The result is, well, the energy required to just store the information is vastly, vastly greater than all the energy contained within the observable universe itself. We're talking something like 10^108 ergs needed compared to maybe 10^178 ergs available.
So you'd need more energy than the entire universe possesses just to hold the data for its simulation.
Exactly. It's not just impractical, it's fundamentally impossible according to these principles. There simply isn't enough energy available in the parent universe, assuming it's like ours, to encode the child simulation.
So conclusion 1, full universe simulation at the Planck scale is out. The paper also mentioned an alternative estimate using the Hawking-Bekenstein formula for black hole entropy, right? Treating the universe like one giant black hole.
Yeah, they did that as a cross-check. It gives a slightly different number for the maximum information, but it's still in that same absolutely enormous 124 bits range.
Still impossibly large.
Still impossibly large, yeah. And importantly, it's still countless orders of magnitude larger than the amount of data handled by our most complex cosmological simulations today, like Illustris, which are already pushing supercomputing limits. So whichever way you calculate it, simulating the whole universe fundamentally seems ruled out by energy constraints.
All right, universe scale simulation is off the table. Let's scale it down dramatically. What about just simulating our little blue planet, Earth? Surely that's more feasible.
You'd think so, wouldn't you? But let's look at the numbers. They take Earth's radius, its mass, calculate its total rest mass energy, EMC node E2. Then they apply the same holographic principle and Bekenstein bound to Earth's surface area.
Okay, so how much information does a max resolution Earth simulation require?
The maximum information content, IMAX, describe Earth down to the Planck scale, comes out to around 10,075 bits. Still a huge number, though obviously much smaller than the universe's.
Still enormous. And the energy cost to encode those bits, even assuming that super cold CMB temperature computer.
The minimum encoding energy, EMAC, license needed, is calculated to be around 10 to 59 ergs.
Okay, 1,059 ergs. How big is that in, like, astrophysical terms? Is that a lot?
It's an insane amount of energy. The paper points out this is comparable to the entire rest mass energy of a large globular cluster, those dense balls of millions of stars. Or, alternatively, it's similar to the gravitational binding energy holding the Milky Way's entire dark matter halo together.
Wait. So just to store the data for a perfect simulation of Earth, you need the energy equivalent of millions of stars, or basically the energy holding our galaxy's structure together.
That's what the calculation suggests, yes, just for the information storage.
That's still completely bonkers.
It is, and it gets worse, because that's just the energy to store one snapshot. The paper argues you'd need to dissipate roughly that same amount of energy for every single tiny time step the simulation takes.
Oh man, so it's not a one-time setup cost.
Not at all. It's a continuous power drain. Running the simulation for any meaningful amount of time would require consuming energy far exceeding, say, the entire rest mass energy of the Milky Way.
Okay, so forget galactic energy scales. We're talking beyond that.
Pretty much. It doesn't seem physically sustainable within a universe like ours.
And what about the physical implications of actually having that much energy concentrated? Doesn't that cause problems?
Huge problems. The paper calculates that if you tried to concentrate the required encoding energy into a region small enough to compute efficiently, its self-gravity would be overwhelming.
It would collapse into a black hole.
It would form a black hole with a mass of over 160,000 times the mass of our sun. Its Schwarzschild radius, its event horizon, would be almost as big as the radius of Jupiter.
So your computer becomes a supermassive black hole the size of Jupiter. That seems problematic for running code.
Extremely problematic, yes.
Yeah.
Keeping this thing stable, feeding it power, dealing with the intense heat and radiation, think accretion disks around black holes, it all becomes astrophysically absurd. The paper even mentions earlier work by Sandberg estimating a realistic Jupiter-sized computer's capacity at maybe 147 bits. That's 27 orders of magnitude less than what this calculation says is needed for full-res Earth.
So, conclusion 2. Simulating Earth at full Planck scale resolution. Also physically impossible due to, frankly, ridiculous energy requirements and the fact your computer turns into a giant black hole.
That sums it up pretty well. Hard no.
Okay. So universe simulation, no. Full resolution Earth simulation, no. But maybe the simulators are clever. Maybe they cut corners. What if they simulate Earth at a much lower resolution? Not every Planck-length detail, but just enough to fool us.
That's the logical next step, and the paper tackles it. The idea is maybe the simulation only needs to render detail down to the smallest scales we, the inhabitants, can actually probe experimentally.
Right. No need to simulate quarks inside protons if we never look that closely everywhere.
Something like that. So what are the smallest scales we've actually tested across significant distances?
Well, the paper mentions particle colliders like the LHC probe tiny distances, like 10, 16 centimeters, but only in tiny localized spots.
Exactly. And ultra-high energy cosmic rays hitting the atmosphere probe even smaller scales, maybe 10, 24 centimeters, but again, only in the upper atmosphere. They don't tell us about the structure deep inside the planet at that resolution.
But then there are neutrinos, those ghostly particles. They go right through everything. How do they set a limit?
That's the key insight here. We've detected very high-energy neutrinos using detectors like IceCube at the South Pole and KM3Net in the Mediterranean. These neutrinos have energies up to PeV levels, 1015 eV, and even higher, and they demonstrably travel straight through the entire Earth.
Okay.
To accurately simulate how these neutrinos interact, or mostly don't interact, as they pass through the planet, requires the simulation's grid, its fundamental resolution, to be at least as small as the effective wavelength or interaction scale of these neutrinos.
So the simulation needs pixels small enough to correctly render a neutrino's path through the whole planet.
Precisely. Based on the highest energy neutrinos observed across Earth, Enschorian 1017V, the paper estimates this minimum necessary resolution, lambda nu, to be around 1.2 by 1021 centimeters. Any coarser than that, and the simulation would likely fail to reproduce the observed neutrino physics.
Okay, 1021 centimeters. That's still incredibly tiny, but much, much larger than the Planck length, which is around 1033 centimeters. So this low-res simulation needs drastically fewer bits, right?
Drastically fewer. They rescale the maximum information estimate by the ratio of the areas, Planck area versus this neutrino scale area. The required information for this low-res Earth Low and plus low drops to about 1.65 by 2051 bits.
Still a big number, but maybe manageable. What's the energy cost for this version?
The minimum encoding energy, low plus low, again assuming CMB temperature, comes down to about 4.3 by 235 ergs.
135 ergs. How does that compare? Is that still astronomical?
It's getting less astronomical. The paper compares it to about 2 minutes worth of the sun's total energy output. Or in mass terms, it's only about 1019 solar masses.
Okay. That actually sounds almost plausible. Compared to needing the energy of a globular cluster, 2 minutes of sunlight seems achievable, maybe?
The initial energy cost looks way more tractable, yes. But wait for it. The real killer isn't the energy storage, it's the processing power. How fast can you actually run this simulation?
The computations per second.
Exactly. The paper brings in Seth Lloyd's work on the ultimate physical limits of computation, often framed using black holes as the theoretical ultimate computer.
Because they pack the most mass energy information into the smallest space.
Right. They represent the densest possible configuration of matter and energy, and thus potentially the fastest possible computation rate, according to some theories.
So even if we use a hypothetical black hole computer optimally designed for this task, can it simulate low-res Earth in real time?
This is where it falls apart again. They calculate the minimum mass black hole needed just to store the 1051 bits of information for low-res Earth. It's tiny, astronomically speaking. But then they calculate the maximum number of operations per second this black hole computer could possibly perform. Even under the most optimistic scenarios, whether the black hole is heated by accreting matter or just emitting Hawking radiation, the maximum operations per bit per second is limited.
Okay.
Now, consider the simulation. To accurately model those high-energy neutrinos crossing the planet, the simulation needs a very, very small time step, delta TT, roughly the time it takes light to cross the minimum resolution distance lambda no. That's about 1032 seconds.
So you need to update the state of 1051 bits every 1032 seconds.
Effectively, yes. That requires an absolutely colossal number of operations per second overall. The paper calculates the total computing power, Pitman's energy, available from the black hole computer, and it's nowhere near enough.
So the simulation runs slow. Like how slow?
Glacially slow. To simulate just 1 second of real Earth time at this low resolution, the black hole computer would need to run for something like 10 to 100 million years.
Million years of computation for 1 second of reality.
Yep. So real-time simulation is completely out of the question. And if you flip it around and ask what kind of power you'd need to force it to run in real time.
Let me guess. Something ridiculous.
Something utterly ridiculous. The power required would vastly exceed the total energy output of all the stars and all the galaxies in the observable universe combined by many orders of magnitude.
Wow. Okay, so conclusion 3. Even the most basic, low-resolution simulation of Earth consistent with our observations is computationally impossible in terms of speed and power requirements.
That's the finding. The timescales are geological, and the power needs are super cosmological. It's just not plausible within known physics.
Okay, the paper seems to build a pretty strong case, but it does address some potential counterarguments, right? What about just throwing more computers at it, massively parallel processing?
They do consider that. But they refer back to Lloyd's results, which suggests that while parallelism can divide the task, it doesn't fundamentally increase the total number of operations per second achievable with a given amount of energy. The black hole computer scenario is already supposed to represent the ultimate parallel processor bound by physics. Making more, smaller processors just makes each one slower, keeping the total operations per second capped.
So no easy fix there. What about relaxing the time step? Maybe the simulation doesn't need to update every 1032 seconds. Could it take bigger time jumps?
They look at that too. What if the time step only needs to be as small as the shortest time interval we can actually measure in a lab, which is much longer, maybe 10-20 seconds?
Would that help enough?
It helps, but not nearly enough. Even with that much coarser time step, the simulation would still run many, many orders of magnitude slower than real time. And the power required to achieve even that slow speed would still be astronomical, comparable to the energy output of entire galaxy clusters or the most luminous quasars. Still not feasible.
Okay. And the elephant in the room for future tech? Quantum computing. Could that somehow magically bypass these energy and speed limits?
The paper argues probably not for this problem. While quantum computers are amazing for certain algorithms, they don't fundamentally change the constraints imposed by space-time geometry, information density limits like the holographic principle, or the energy cost of computation. Landauer's principle still applies. The black hole computer model is often considered a kind of ultimate quantum computer already, pushing those limits. So quantum computing doesn't seem to offer a loophole around these specific astrophysical constraints.
Right. It's not just about clever algorithms, it's about the fundamental resources needed. The paper also briefly asks, what if the holographic principle underestimates the information needed?
Yeah, it's a fair point. If reality is actually more complex informationally than the holographic bound suggests, then all of these calculations are underestimates. The energy and computational requirements would be even higher, making simulation even less likely.
So, strengthening the impossible verdict.
Pretty much. While we can definitely compress descriptions of large-scale things, like the cosmic web in our simulations.
Using statistics and averages?
Exactly. But a truly error-free simulation, down to the fundamental scales. That seems to demand this huge information content, maybe even more than holographic estimates.
Okay, so this really seems to shut the door on the idea of us being simulated by a universe like our own, perhaps run by our descendants or some such.
It makes that specific scenario look extremely unlikely based on current physics, yes.
But then the paper takes this speculative turn. What if the simulators live in a universe with totally different physics?
Right. This is where it becomes highly speculative, moving beyond direct calculation. They performed a kind of exploratory study using Monte Carlo simulations.
Meaning they just randomly tried out different physics?
Sort of. They varied the values of the fundamental constants, the strength of gravity, the speed of light, c, Planck's constant h-bar, Boltzmann's constant kb, the proton mass, even the universe's expansion rate over like 40 orders of magnitude around our values.
Wow, okay, tinkering with the basic rules of reality.
And they looked for combinations of these constants in these hypothetical universes that might, just might, allow a low-resolution simulation of something like Earth to run at least in real time relative to that universe's lifespan. And using what might be considered a reasonable amount of power in that universe's terms, they sort of arbitrarily scaled 1 gigawatt based on the proton mass in that universe.
Okay, that's quite a leap. Did they find any potential candidate universes where simulation might work?
The results, illustrated in some figures in the paper, suggest that, yes, there might be combinations of fundamental constants wildly different from ours, where such a simulation could potentially be feasible according to their criteria.
So universes where maybe light is much slower, or gravity is weaker, or particles are heavier.
Or quantum effects are vastly different, yeah. Combinations that would make the universe operate in a fundamentally alien way compared to ours.
But the key point is, these simulating universes would not be like ours.
Absolutely not. They would be drastically, fundamentally different.
Right.
So while simulation might be possible under some exotic physics, it completely rules out the common sci-fi trope of our descendants in a slightly more advanced version of our universe running the show.
And simulation by a universe with totally alien, perhaps unknowable laws.
That, the paper rightly concludes, is essentially unfalsifiable. It's beyond theoretical speculation, let alone scientific testing.
Yeah.
They use the analogy of Pac-Man characters trying to figure out the physics of the arcade machine they live in. They just lack the concepts.
Right. It becomes philosophy or faith at that point, not physics.
Precisely.
Okay, let's try to wrap this up. The main conclusions seem pretty clear. Simulating our entire universe by a similar universe. Impossible due to energy information limits.
Correct.
Simulating just Earth at full resolution. Also impossible, needs galactic scale energy. Computer becomes a black hole.
Also correct.
And even a low resolution Earth simulation. Just good enough to fool our neutrino detectors. Computationally impossible, takes millions of years for 1 second, needs more power than all the galaxies combined.
That's the trifecta of impossibility based on their analysis, yes.
So the implication for the classic matrix scenario simulation run by beings in a universe like ours is that it's highly, highly improbable based on known physics.
Extremely improbable, bordering on physically ruled out.
But there's that tiny, highly speculative window left open for simulation by universes with vastly different fundamental constants.
Yes, but those universes would be unrecognizable to us, and the nature of such a simulation is purely conjectural. And simulation by something with completely different rules altogether is beyond science.
It's fascinating, though, how pushing this simulation idea forces us to confront these fundamental limits of information, energy, computation, and the structure of reality itself.
Absolutely. It's a great example of how even exploring seemingly outlandish ideas can sharpen our understanding of the physics we do know. It highlights the profound connections between computation, energy, gravity, and quantum mechanics.
So even if we're pretty sure we're not in a simulation based on this analysis.
The exercise itself is valuable. And as the author notes, even without being simulated, the universe holds more than enough genuine, solvable mysteries to keep us busy for a very long time.
A fantastic point to end on. This has been a truly mind-bending deep dive. Thanks for walking us through it.
My pleasure. It's definitely food for thought.
And thank you for joining us on the Deep Dive.